Ready to learn? Hello, welcome back. So here's the new video that you guys have asked for. I understand that we've had a lot of problems with combining like terms, so I thought I'd take a moment to go on ahead and slow that down for us just a little bit. Sometimes the details are a little bit too important to just skip over, and we do cruise in class. As a reminder, tutoring every morning, 7:30 to 8:12. I no longer have morning duty this week, so anybody's welcome. Just let me know the day prior. I've also put a link down there regarding where I got some of these problems from. You can self-generate your own worksheets. They come with the answers. That way, if anybody wants to help you work these problems, you guys both have answers and problems together, and you don't have to worry about creating your own. That being said, let's get on with the show, shall we? Ready to learn? Combining like terms turns out to be a whole lot like working with our fractions. Now, when we look at this equation here, we intuitively know that there is something we have to do here because we know that these denominators, one is 2 and one is 4, and we can't just add them together because they represent different things. This represents one piece cut in half, whereas this represents one piece cut into fourths. And so we just can't add 1/2 plus 3/4. We've got to do something to it, and we call that finding the greatest common denominator. Now, y'all might just intuitively know that we need to multiply both sides by 2, or the numerator and the denominator by 2, because that would get us to a common denominator of 4. And so that would give us 2/4 plus 3/4. And now remember, that is still the same values. But because we now have them in like positions, we can easily do that, and we see 5/4. Now, the reason I wanted to draw this out for you is because this is very much like adding like terms. We have to have the same piece before we can actually do anything with them. Okay, so before we get into this discussion too much, I want you to understand some terms here. You may notice that my screen keeps changing. I'm actually learning how to edit, and I'm not that good at it yet. I promise, less cringe as we go. So this is actually the last thing I've recorded for the video. Regardless, so a variable, because we need to understand the definition, a variable is a placeholder for an unknown value. The value of a variable can move up and down the number line, and it's usually represented by a letter. So remember when we were playing on the number line, Mr. H, I'm not bound down to 1 or 2 or 3. I could be anywhere up and down that number line. And this week, we're going to talk about inequalities, which means I'm not just at one spot, but I could actually be all of these past this point, or all of them past that point. Just go with it. It'll make more sense to next week. Now, in contrast to that, a constant is a value that cannot change, and it's represented by a number. So remember, we danced and we said that whenever we were dancing on the number line, that 2 has to stay on 2. -5 has to stay on -5. Those are constants. They cannot change. Now, a coefficient, that's a new word for us, and I heard some of you guys asking about it. Maybe this is the part the book forgot to tell you, but a coefficient is nothing more than the number in front of the variable. It represents a multiplication or the number of times that a variable should be counted. For example, because we all know multiplication is repeated addition. So if you were to see, for example, 2x, well, we know that that is nothing more than x times x, or x plus x, because we have 2 x's. If you were to see 3p, well, then you know that that's really just the same thing as p plus p plus p, because we have 3 p's. So the coefficient is just this number out front here. Now it is important to note the absence of a coefficient means that there's a coefficient of 1. So if I was to write just x, that is 1x, or just y, that is 1y. Now, a term is something that is either added or subtracted in an expression. It can be expressed as either a constant, a variable, or a coefficient and a constant and a variable. So you would see something like 2x or 2. Either of those could be terms in an algebraic expression. Now, like terms are terms which share the same variable to the same power. For example, x squared is the same thing as x squared. X is x, y is y cubed is y cubed, but notice y and y cubed are not like terms. Now the connection I want you to make here with the previous problem of fractions, terms are going to be just like that common denominator. We can't do anything with them unless they're the same. So the exception here is there's nothing we can really do to the variable to turn it into the other thing. So we just have to accept that they're going to remain separate. So let's dive into this. 9x plus x. Let's take a quick look at this one. So whenever we're drawing our models, I've been having you draw out all of the x's. So 9x, remember that is just telling us we have 9 x's. And we are going to add it to 1x. Well, that's easy enough. This is an old school kindergarten problem, isn't it? What if the x's were apples? In kindergarten, I'd ask you, Johnny has 9 apples. Sally gives him 1 more apple. How many apples does he have? Well, he's got 10 apples. Except now in the 6th grade, we're going to call it x, and we're not going to tell you exactly what an apple is. An apple could be 1, an apple could be 5. I mean, maybe the apples are actually grapefruit. The point is that we can add them together and count it. I want to pause here for a minute. Actually, I want you to push the pause button because you're going to try this one. 4y minus 7y. So go on ahead, pause, and take a moment. Okay, and back at it. So did you get it? Let's see what we got. Let's see if this works. So if you're still having problems with the concept of like terms, I would always encourage you to go on ahead and draw the model. Now, I like to do the red as negative y's because that reminds me that it is the opposite of y. Now, what happens when I take a positive number and I add a negative to it? Well, that's easy enough. That gives me 0. So I can essentially, that y and that y are a pair, this y and this y are a pair, this y and this y are a pair, this y and this y are a pair. So what am I left with? Well, I have 1, 2, 3 negative y's. Well, then I would just write equals minus 3y. And that is the correct answer. I hope you got it. If not, go to Math Aids, think about it, and don't be afraid to draw these models because these models are exactly how we're going to get the understanding of the representation of how we wind up on the wrong side of 0 on that number line. So let's take a look at another problem here. Get the cursor up. There we go. All right, so this one's a little bit more difficult. We're going to have to do the distributive problem. Now remember, with the order of operations, we always have to do parentheses first. So we have parentheses here. I need to go on ahead and get rid of these parentheses right here and here. And as we've learned, the only way I can do that is to go on ahead and distribute. So I'm going to distribute this 8 into the 2x, and then I'm going to distribute the 8 into the 4. So first things first, 8 goes into the 2x, so 8 times 2x, well, 8 times 2 is 16x, and then I keep my plus sign, so I drop that down, and then I have my 8 times 4, and we know 8 times 4 is 32. And then I'm going to rewrite the rest of the problem. Now, remember, like terms don't always have to have a variable. Okay, so I could draw the model here for 16 x's, but I'm going to assume that because there's no other x's, you guys realize that we can't really do anything. So let's go on ahead and drop down that 16x. But now, the lack of anything behind these means that those constants are like terms. And I don't want you overthinking this because this is natural math. This is stuff we've been doing. 32 plus 5 is 37. So your simplified algebraic expression in this case is 16x plus 37. All right, I hope you're ready for the challenge. Try this one. Push pause. I don't think you might have pushed pause. I know a lot of you did, but I know at least one of you out there just went on ahead and watched to see what happens. Okay, so in this case, we've got another complicated problem that requires us to do stuff in a weird order. So again, we know order of operations. Oh, I see parentheses. I got to take care of these parentheses. So I need to multiply first. Now let me write my problem down till I get to that. Okay, so 3 times x squared. Well, that's going to be 3 times x squared. And now I'm going to keep my operation plus, and then I'm going to do my 3 times 2. Well, 3 times 2, that's 6. And then I'm going to keep my operation. And then I'll just rewrite the rest of my problem. X squared. Okay, so now I have like terms that I can combine. Like I had said before, we know that the lack of a symbol is simple math. So we have 10 plus 6. So let's rewrite that in a different color. All right, looks like purple it is. 10 plus 6. Well, we know 10 plus 6, that's 16. And then I have my 3x squareds, x squared and x squared minus 1x squared. Well, if I subtract 1x squared from these x squareds, what do I have? I have 2x squareds. So the simplification of this is 16 plus 2x squared. And for those of you that want to write things in a more professional order, 2x squared plus 16, because we will always put the variable to the left, and it will always be the variable with the highest exponent. Let's move on. So this is probably the most complicated problem you're going to see in the 6th grade. Don't panic. It's easy. It's just adding and subtracting. Don't trip. Let's take a look at it. What do we have? And let's use our colors because colors help us see things. So we have y, and then I have another y. Okay, I'm going to switch colors now. I have a 5, a 3, and that's all of those. And now I have an x, and an x, and a x. Oh, no, see, this has got an x squared. So it is its own term. We're going to give it its own color. So now all we have to do is combine the like terms, and we'll combine them using the operation preceding that term. So we have 3y minus 2y, because that subtraction symbol is in front of it. So what's 3 minus 1? Because remember, we have an understood coefficient of 1. 3y minus 1y. Well, 3 minus 1 is 2y. And now I'm going to go with my next symbol, which is a plus, so my operation. And then let's look at, okay, so we'll look at red, and I've got 5, and now the symbol preceding this 3 is a subtraction symbol. So 5 minus 3 is 2, and then I'm going to swap to my next color. I have 2x, and the symbol preceding, oh, look, I forgot a step. I got to bring down this plus. The 2x, and then the symbol preceding that other 4x is an addition, so I'm going to add it. 2x plus 4x, Well, that's 6x. And then my last lonely one out here is this x squared, and the symbol preceding that is an addition. So now I've got my simplified equation. For those of you who really truly want to get mathematical with it, we also go in alphabetical order. So it's going to be x squared plus 6x plus 2y plus 2. And we know we can do this because addition is commutative. Both answers are correct. In fact, you could put these terms in any order you want. You could wash them around in any way. And as long as everything was positives and additions, you're golden. So now you guys got an idea what's coming, right? Your turn. Give this one a shot. I'm going to have to get out of the way. So now that I'm out of the way, I want you to go on ahead and give this a try. Okay, I hope you gave it a try. Now let me work with it, and let's see what if we both came to the same answer. Now, I'm going to use the colors so I can point out that I can find the terms quickly and easy. I've got an A. That's not an A. That's not an A. There's me another A. Not A, not A, not A. Okay, so now I'm going to switch colors again. I've got a B. There's another B. And nope. All right, one more color. Let's go. We've got a constant and a constant. And then I've got one more term, and it's right there. So now all I got to do is go back and look at my terms. So I've got 7a, and now I'm going to use the operation preceding that term. So 7a plus 6a, well, 7 plus 6, 13a. Now I'm going to take this operation because it's my next operation, and then I'm going to look at my red. Oops, my red. So I have 2b, and I'm going to take the symbol preceding minus 3b. Well, 2 minus 3, that's going to be a negative 1b. Now, because that negative 1 can make things look a little funky, I'm just going to make it negative b, because remember, that's the way this works. 1 is inferred. Okay, so now let's come on back and we'll look at our 2's. Now I have a negative 2. Okay, so my operation will be a minus. So then I go 2, well, actually I've got negative 2 plus, what do I have? Plus 6. What's negative 2 plus 6? Well, that is a positive 4. Okay, and then our last term that we've got to deal with is a plus c. So I'm going to go plus c right there. And you should have come up with 13a minus b plus 4 plus c. And for those of you who want to write it truly algebraically, 13a minus b plus c plus 4. So I'm glad you watched. Hopefully I get this edited right. And as a reminder, tutoring every morning. This was Combining Like Terms. Hope you learned. I had fun. That's all that matters. Are you ready to learn? Knowledge is power. Ready to learn!